Welcome, Class 12 students. Okay, get ready, because today we are taking a seriously fantastic journey. We're stepping right out of the dry pages of your textbooks and diving straight into the real-world chemistry of smells, flavors, and the incredible materials that make up our modern world. Today's explainer is all about a deeply fascinating group of organic compounds. So let's jump right in. I want you to think about this for just a second. What on earth do the sweet smell of vanilla, the spicy kick of cinnamon, and that sharp, super distinctive scent of nail polish remover actually have in common? I mean, at first glance, absolutely nothing, right? But if we put on our chemistry glasses and zoom way into the molecular level, we're going to find a very specific structural feature hiding in all of them. We are hunting for a molecular signature today that literally changes the way we experience the world around us. Well, that molecular signature brings us right here to Unit 12 of your syllabus, aldehydes, ketones, and carboxylic acids. Now, I know your board exams are always looming in the background, but let me reassure you right now, this isn't just pure theory. The exact reactions and structures you need to master for those exams are the exact same ones responsible for the fragrances in your perfumes and these solvents sitting in your cabinets. Mastering this unit means mastering a massive piece of real-world chemistry. So here's our roadmap for this explainer. We'll meet the carbonyl group, look at names and structures, explore methods of preparation, dive into key chemical reactions, and finally, check out some everyday, real-world uses. Let's start right at the beginning with Section 1, Meeting the Carbonyl Group. Let's introduce the star of our show. Before we even draw this thing out, let's appreciate what it actually does out in the real world. The widespread presence of this functional group in plants and animals is literally what adds beautiful fragrances and flavors to nature. When you smell the rich, sweet aroma of vanilla beans, you're interacting with a molecule called vanillin. That spicy, warm kick of cinnamon, that's cinnamaldehyde. And the really pleasant scent of meadowsweet, salicylaldehyde. Nature is essentially one massive organic chemistry lab, and it loves using this specific molecular tool to create sensory experiences for us. So, what exactly is this molecular tool? It's the carbonyl group, which is quite simply a carbon atom double bonded to an oxygen atom. But notice the polarity at play here. Oxygen is much more electronegative than carbon, which means it greedily pulls the shared electrons towards itself. You can kind of think of it like molecular magnetic poles. The carbon becomes electron deficient, acting as an electrophilic center, a Lewis acid. The oxygen, meanwhile, becomes electron rich, acting as a nucleophilic center, a Lewis base. This creates both neutral and dipolar resonance structures, making carbonyls highly reactive and way more polar than things like ethers. This polarity, it's the absolute engine driving all of their chemical behavior. Moving on to Section 2, Names and Structures. If they all share this carbon-oxygen double bond, how do we actually tell them apart? It all comes down to what's attached to that carbonyl carbon. In aldehydes, the carbonyl group is parked at the very end of the carbon chain, meaning it's bonded to at least one hydrogen atom. We name these by dropping the E from the parent alkane and adding the suffix -al, like ethanol or propanol. In ketones, the carbonyl group is sandwiched right in the middle, bonded to two other carbon atoms. We name these using the suffix -one, like propanone, which you probably know better as acetone. Having this simple structural distinction rock solid in your mind is absolutely crucial before we start making and breaking these molecules. All right, on to Section 3, Methods of Preparation. Let's look at how chemists actually build these molecules in the lab. Let's start with our first set of methods, which builds perfectly on what you've learned in previous units. We often start with alcohols. By carefully oxidizing a primary alcohol, we get an aldehyde. If we oxidize a secondary alcohol, boom, we get a ketone. Another really fantastic industrial method is dehydrogenation. If you pass volatile alcohol vapors over a heavy metal catalyst, like silver or copper, it actually strips away hydrogen gas, converting primary and secondary alcohols directly into our target aldehydes and ketones. Just to put that into perspective, this exact dehydrogenation process is how the industry churns out millions of tons of formaldehyde for manufacturing every single year. Now pay close attention here because these next two named reactions for preparing aromatic aldehydes are absolutely massive for your board exams. Please take a mental note of these two. First up, the Ittard reaction. Here, we use a very specific reagent, chromyl chloride, to gently oxidize the methyl group of toluene. The magic here is that it stops right at the aldehyde stage to give us benzaldehyde, rather than over-oxidizing all the way to a carboxylic acid. Second, the Gatterman-Koch reaction. This is just a brilliant way to slap an aldehyde group directly onto a benzene ring, using carbon monoxide and hydrogen chloride gas with a catalyst. Both of these are huge for your exams, and they happen to be exactly how we synthesize the artificial almond and cherry flavors you taste in your favorite candies and baked goods. Which brings us to Section 4, Key Chemical Reactions. Let's see how these molecules behave when we start mixing things up. First, take a look at these three compounds. They all have the exact same molecular mass of 58, N-butane, propanol, and acetone. But look closely at those boiling points. N-butane boils at 273 Kelvin, while our aldehyde and ketone boils significantly higher at 322 and 329 Kelvin. Why is that? Well, it goes right back to that polarity we talked about earlier. The strong dipole-dipole interactions in the carbonyl group mean these molecules stick together much tighter than standard hydrocarbons, requiring way more heat energy to pull them apart. This specific property is exactly why acetone evaporates so incredibly fast, making it the perfect quick-drying solvent for everyday things like paint and nail polish. Plus, the smaller members of this family are highly soluble in water because they can actually form hydrogen bonds with water molecules. Because that carbon center is electron deficient, it absolutely loves to react with nucleophiles, which are species that have extra electrons to donate. Notice the pattern in these nucleophilic addition reactions with ammonia derivatives. You don't need to memorize this entire set right this second, but just look at how the nucleophile attacks, water gets eliminated, and we form these beautiful double-bonded derivatives like amines, oximes, and hydrozones. This pattern is a massive staple of your organic chemistry syllabus, so getting comfortable with it is a game changer. But here's a fun, practical mystery for you. If I hand you two completely unlabeled test tubes, one has an aldehyde and the other has a ketone, they often look identical. They might even have really similar boiling points. So how do we tell them apart in the lab, quickly and visually? Enter the Tollens test. Honestly, this is basically a chemistry magic trick. We exploit a key difference in their chemical personalities. Aldehydes are very easy to oxidize further, while ketones are super stubborn and require really vigorous conditions. If we warm our unknown sample with Tollens reagent, which is essentially ammoniacal silver nitrate, an aldehyde will easily be oxidized to a carboxylate anion. And in the process, the silver ions are reduced to solid silver metal, which coats the inside of the test tube, creating a stunning, bright silver mirror. Ketones, they do absolutely nothing in this test. Mystery solved. In fact, this exact chemical reduction is historically how artisans created the reflective silver backing on vintage glass mirrors. Pretty cool, right? Now, we also need to know how to go in reverse. Instead of adding oxygen, what if we want to completely strip it away? We have two famous reduction reactions for this. The Clemmensen reduction, which uses zinc amalgam in an acidic medium, and the Wolff-Kishner reduction, which uses hydrazine in a highly basic medium. Both of these named reactions do the exact same incredible thing. They rip the oxygen atom completely off the carbonyl group and replace it with two hydrogens, converting it straight back into a plain old standard hydrocarbon chain. Before we wrap up the reactions, I want you to take a look at these in-text questions right from your syllabus. When you're reviewing this explainer later, pause right here. Test your knowledge. For question 12.4, remember that reactivity in nucleophilic addition depends on steric hindrance, basically how physically crowded that carbonyl carbon is, and the electronic effect, meaning how much positive charge is actually sitting on that carbon. Ketones are more crowded and have two carbon groups pushing electrons toward the center, making them way less reactive than aldehydes. Give these a try on your own. Let's bring it all home with Section 5, Real-World Uses. Time to connect all these textbook concepts to everyday applications. As we've seen throughout this explainer, carbonyls are literally everywhere. Whether it's formaldehyde preserving biological specimens in your school lab as formalin, or making hard bakelite resin. Or maybe it's acetaldehyde, helping manufacture polymers in acetic acid. Or, of course, acetone, acting as a highly effective and quick-drying industrial solvent. Whether it's the glue holding your furniture together, the plastics in your devices, or the perfume you spritz on in the morning, aldehydes and ketones are the molecules making it happen. Which leaves me with just one final question for you today. Now that you know how they smell, how they act chemically, and what they're used for industrially, where will you spot the carbon-oxygen double bond hiding in your own home today? Take a look at the ingredients in your pantry, your bathroom, your cleaning supplies under the sink. I challenge you to look at your world and your upcoming chemistry exam through this completely new, practical lens. Thanks for learning with me today, and keep exploring.